I don't want to say that this is a review, okay? So I don't want you to look at this set of problems as being like the only things you need to look at, but it just gives you, well, I had a discussion with one of my colleagues and we were talking about exam reviews and everything else, and we said, well, you know, the chapter review is one place you could start if you're going to review. You could go and take a look at the chapter review. So what I did is I picked some problems within the chapter review that I thought were, in terms of topics, the same topics that would be on the test. And even narrowed it down to the 7 topics that would be there, which are differentiation of inverse trig functions, exponential and log functions, and within that there's logarithmic differentiation. So I gave you some problems, number 17 through 43, page 200, that you can look at. But when I did that initially, I completely forgot that we haven't talked about hyperbolic trig functions or inverse hyperbolic trig functions. So you need to omit number 27, 39, 41, and 42, because those all have either hyperbolic or inverse hyperbolic. That's Cal 2. Cal 2, you'll do that. And then on page 201 is L'Hopital's rule. I say do 61 through 76, or take a look at 61 through 76. And number 65 on that page has a hyperbolic trig function in it, so chunk it. And then after we get through those topics, there's closed interval method, and then increase, decrease, concavity, some problems you can look at. And then 5 and 6, there's not supposed to be a 7 there. Oops. That's just supposed to say Newton's method and then a page. We have not talked about 5 and 6, but that's what I'm going to talk about today.
We're going to be bonus, right?
What's that?
We're going to be bonus.
Yes, but these are problems that you can look at. Okay? But I do want to check those sections off and say that we've completed them. And we can do them pretty quick. They're not 45-minute problems like the curve sketching was.
Is there anything like new material? Or?
It is new. Yes. Why?
Well, I was just wondering.
Yes.
You know what I meant, like in concept.
Yes, it is. Well, yeah, they are it's very different than what we've been doing as far as like, we're not going to be doing concave up, concave down, all that, no. But it's all tied into an applications of the derivative.
Has to do something with differentiation.
Pardon?
Has to do something with differentiation.
Yes, yes. All right. Y'all okay right there?
Good.
Yes? You sure? All right. So the test is on Tuesday, right? Make sure you look over your homework. You know, look at the problems I assigned for homework, the problems that I did in class that, you know, examples of L'Hopital's rule, logarithmic differentiation. Is everyone clear on what the topics are going to be? Differentiation, right? Logarithmic differentiation, L'Hopital, which there's a lot there. Closed interval method, increasing, decreasing concavity. I'll give you a problem like that, but I won't ask you to sketch it. Just show me you can figure out where a function is going up and down and where it's concave up, concave down. So, and then mean value theorem and Newton's method. Let's go through it first, because if I might go through this and you might actually be like, yes, I want that on the test, because the problems are pretty easy to do. All right, so you might actually prefer that over a longer test that has other stuff in it.
What chapter
It's
is
chapter 4.
Chapter 4 and 5.
Well, let's see.
Because I thought we were doing 4.2 today.
4.2, yes, 4.2 is mean value theorem.
Which is Newton's method.
That's new, yeah.
Oh, okay. I was
Yeah.
confused. I was like,
But I decided to do Newton's method at the same time. We're going to do that also. All right, we ready? Let's get down to business. All right, the mean value theorem is this section that I said we could skip and come back to because it really didn't have anything to do with like sketching curves. So what the mean value theorem is about is about this theorem that's really, really upset, right? That's humor, come on. It's Thursday, let's go. So the mean meaning average value. This theorem has to do with the average value of a function. And to actually motivate this idea, we're going to start with a different theorem that is called Rolle's theorem. And it's the good thing about the mean value theorem is that it's very visual. You can look at it, you can kind of nod your head and be like, yeah, that makes sense. All right, so let me do Rolle's theorem first, then we'll get to the mean value. Rolle's theorem says, let f be a function such that the following three things are true. All right? So first of all, f is a continuous function on a closed interval. That means if I draw this, let's say this is my x and y axes. Let's say I have some x value a, some x value b, that when I draw this, I don't have to pick up my pencil, right? It's continuous on that interval. Also, this is important, that it is differentiable on the open interval AB. That means inside, between A and B, the derivative exists at every single point. The derivative exists. That means no corners, no cusps, no vertical tangents, no jumps, but we can't have jumps because we had to be continuous. So, and the last condition, f of A equals f of B. Now this is the most important condition that we need. This is not saying for every value of x. This is saying the value of the function at the left endpoint is equal to the value of the function at the right endpoint, which means that the two endpoints are the same height off the x-axis. So let's say this is f of A. F of B would be here, right? See, they have to both be equal, the same height. So now I come in here and I try and draw a continuous function connecting those two together. And you can imagine different ways you could do this, right? I'm just going to make one up. So, that good? And you could have done many different things. The theorem says this. Rolle's theorem says that, bring this up just a little bit. I don't know, can you all see that bottom line here? Everyone see that? Okay, Rolle's theorem says if these three conditions are met, then there must exist a number C. All right, there must exist a number C inside AB. So inside your closed interval, somewhere in there, there has to be a number C such that the derivative at C is 0. So the derivative is the slope of the tangent line, right? And we're saying somewhere in here, there's got to be somewhere that as I move along the function, right, the slope of the tangent line must be 0. Do y'all see it's right there? Okay, so there's some point C in here, guaranteed that the slope of the tangent line at that point is 0. Does it make sense to you that there would be absolutely no way you could draw this where that wouldn't happen? Can anyone think of a way I could draw it where it wouldn't happen and still have a continuous function that's differentiable? The theorem says there's not a way that you can do it, but think about it. I mean, you can't try and draw something different in here. What if I did something like this? That, right? I would actually have two places, wouldn't I? I would have one here and here. Slope of tangent line would be 0. I would have two C's. Make sense? It would be impossible to have that not happen. What about straight across? That's continuous. That's differentiable. Okay. So what's the slope of the tangent line? 0. Where? Everywhere, right? So actually every point would be valid. This theorem guarantees us at least one. It says there exists a C. It doesn't tell us how many there are, but it guarantees the existence of at least one. All right? We might have 2, like the red one had 2, and it might be an infinite number of points like the straight line. Does that make sense? Okay, so I'm gonna erase this and I'm gonna draw it again. Because I want to illustrate something. Okay, no, remember this. Two endpoints, same value. I go up, come back down, there we go. Then I have here, the slope of the tangent line is 0. What I want you to realize is that this theorem is really not talking about, or I should say, in order for us to get to the mean value theorem, which is the one that this section is about, I don't want you to look at this slope of this tangent line as being 0, even though it is. I want you instead to look at that tangent line as being parallel to the line connecting the two endpoints. So what's the line connecting the two endpoints? What's the slope of this line? 0, right? The slope of that red line is 0. So another way I could have said this theorem is that if f is continuous on a closed interval, differentiable on the inside, and the two endpoints are equal, then there exists a number c somewhere in here such that the slope of the tangent line here is equal to the slope of the line connecting the two endpoints. And because the two endpoints have the same y value, that would be 0, wouldn't it? Yeah? Understand the difference in the perspective? Slope 0 versus slope parallel to this. Okay. No questions? Yes?
Can that work the same way if you have two tangent lines that are oblique?
How do you mean? I'm not sure I follow you.
Like say the function does something and then you can have two oblique tangent lines with the same slope.
You mean on the function itself?
Yes.
You can have, I'm not sure I understand your question. Are you saying if I have a function, can I have two tangent lines that are parallel to each other within the function itself?
Right.
Yes, that could happen.
And would that apply to the...
That would not apply to this because this is saying that as long as the two endpoints are the same height,
Okay.
then there's got to be a point in here where this is going to run parallel to the line connecting these two. But I think you actually might be leading into the mean value theorem. I'm just not sure I'm interpreting your question. So let me show you the mean value theorem now. The mean value theorem simply states the first two conditions are still there. Okay? F is continuous on a closed interval. It's differentiable inside. But we're going to remove the condition that the two endpoints have to be the same value. So let me try and draw this for us. Let's say I have a continuous function on a closed interval. Here's A, here's B. But now let me take away the condition that these two heights have to be the same. So let's say I go from here and let's change the height over to this, right? Now let's draw a continuous function connecting these two. Any way I want. That okay like that? What do you think the mean value theorem says?
It's not a mean value theorem.
Parallel, what do you mean?
There's going to be
There's going to be somewhere in here.
yeah, so like if you were to draw a straight line from A to B.
Ah, there you go. That's the key.
It's parallel to
Very good. So this theorem is saying, look, if we connect these 2 points together with a line, which we actually call the secant line, this is called the secant line, right? Because it connects 2 points, it's called the secant. If you have a tangent line, that's at 1 point. So the theorem is going to say that there should be somewhere in here where when I go up to that point and look at the tangent line, it's not going to be equal to 0, it's going to be equal to what? The slope of this line. Okay, so there's somewhere in here. Let's see, where is it? Let me move this along. This is my tangent line on my curve. If I start going, do you agree it's going to start doing this? And somewhere around in here, right? Somewhere around in here, I'm going to get to a point where I'm parallel to the red line. So somewhere in here, I should be parallel. I missed it. Oops. There. Right? Somewhere in there I should be. So there should be some C in here where I have that happen. Right? Now, one way you could justify this is, here's Rolle's theorem, right? There's Rolle's theorem. And what I'm saying is that in Rolle's theorem, this tangent line must be parallel to this line connecting the 2 points. If I take this and I move this right point up so it's no longer the same y value, you see everything just shifts and rotates? And it's the same theorem but without the condition that the two endpoints have to be the same. Or if you want, you can just kind of like turn your head and you're back to Rolle's theorem, aren't you? That's all it is. Turn your head, that's Rolle's theorem. Go like that, your mean value theorem. All right. Now, the reason they call it the mean value theorem is because when you connect the two endpoints of a graph together, it's actually giving you the average of the function. So what I can do to illustrate that is draw you another picture and put something on this that will kind of make more sense. Like, let's say we had a graph where this was time and this was distance. And let's say time was measured in hours and distances in miles. And let's imagine we're going to drive our car. Okay, so we start out, we've got our stopwatch on, we're at home, and we're going to start the clock. And we start driving, and then eventually we stop driving after a certain amount of time, right? Let's say after 2 hours. And we go a distance of 80 miles. So we went 80 miles in 2 hours. What was our average speed? Our average speed was 40 miles per hour, right? You can get that by connecting these two points together and finding the slope of that line. The slope of this line would be rise over run, wouldn't it? What's your rise? 80. What's your run? 2. 80 divided by 2 is 40. So your average speed is equal to the slope of the secant line, right? Which in this case is 40. According to the mean value theorem, there has to be some point in here, right, between 0 and 2, where I should be parallel to that. Which means somewhere in here, I don't know, maybe about right here, somewhere about right there. Right about here, somewhere, don't know. The slope of the tangent line was parallel to the slope of the secant line, which would mean what in terms of this word problem? At some point while you were driving, you had to have gone your average speed.
Can you have multiple?
In it, yes, you can have multiple, yes. But the mean value theorem guarantees it. Guarantees 1. And also notice that the mean value theorem guarantees that it's going to happen inside. It is not going to happen at the endpoints. That's also key. The theorem guarantees that you'll be going your average speed, or your, yeah. I want to back up. The mean value theorem says as long as the conditions are met, continuous function, differentiable on the inside, there has to be somewhere inside where you will achieve your function's value, average value. Somewhere in there, the slope of the tangent line will be equivalent to the slope of the secant line. All right? So if you go and you average, you average 40 miles an hour driving, at some point you had to be going 40 miles per hour. Looking down at your speedometer, at some point you had to have seen 40 miles per hour. Unless you can somehow transport over space and time, like from one place to another. But that would be a discontinuity, wouldn't it? Your function would no longer be continuous. You have a jump in the graph. Yes?
I don't know how long ago it was you asked us a question about 2 cars racing.
Yeah, we're going to answer that today. We're going to answer that today. Yeah. Yeah, I'm leading into that. Yes. Okay, so let me write down, or no, I won't write it down because it's right here. Oh, you know what, I will, because it didn't come out. I had some problems with it yesterday.
End up at the same time.
So here's what the mean value theorem says. Mean value theorem, MVT, says, first of all, if f is continuous on the closed interval AB, f is differentiable on the inside, then there exists, I'll put at least one C inside AB such that the derivative of the function at C, that's the slope of the tangent line at C, right? Must be parallel to the slope of the secant line, right? Yes?
So that is, might have already answered this question, but could that involve the endpoint? Or does it have to happen inside?
It has to be inside, and I'm glad you mentioned that. Yes, look, the mean value theorem says you have at least one value C in AB. That means not at the endpoints. Or else I would have put brackets here. That's critical to the theorem.
The reason I ask that is because, like, you have initial speed. You have initial speed or initial velocity. Is that, I guess if that's just, like, if you just have acceleration at one point, you're going to have an average speed and average. Because if it's constant, it's not going to matter, right?
If your speed's constant
Right.
the whole time,
Yeah.
if your speed was constant the whole time, then your graph would look like a straight line, because your slope of your tangent line would be your speed, would be constant throughout, wouldn't it?
Right.
And then your average speed is you're going your average speed the whole time. So does there exist at least one point in here where you're going your average speed? The whole time you are, right? So there's at least one point. In that case, yes, the endpoints would be valid. You would actually be going your average speed at the endpoints. But the theorem says, look, you're guaranteed at least one inside also. It doesn't have to happen at the endpoints. The theorem says that you're going to have one point at a minimum, 1 point inside where you have to go your average speed. So if you try and draw this any other way, no matter how you get to there, no matter how you do that, there's got to be some point in here where your tangent line on your curve will be parallel to that line, somewhere.
As long as it's continuous.
As long as it's continuous, yes. And as long as it's differentiable. Here's an example. What about this? I'll put it on top of this.
Well, it's not differentiable.
Yeah, you see, you're not that the mean value theorem, you throw it out the window for this one. Because you're never going to be parallel to this black line. You start out here, you go up, right, and then all of a sudden it flips over, now you're negative. You're never going to be parallel to that. But look, that's a cusp. And you must be differentiable all the time. At every point inside, you have to be differentiable.
So this has good applicability, like instead of averaging, if you didn't know what the numbers were and you just wanted to find the average of something that you have, you're able to graph it out, just pull that parallel line, and that will give it to you.
The implications of this theorem would blow your mind. Most of the theorems that we use in mathematics, the proofs for them rely on this theorem. It's a critical theorem to prove other theorems. Because what you can do is instead of looking at what's happening to a function on an entire interval, you know that there's some point in there where you're going to still maintain that secant. You're guaranteed that existence, and you can just use that point instead of looking at the whole interval. It's good stuff. It's a major theorem. It's a major theorem. All right. So I kind of didn't finish this. We're guaranteed the existence of at least one point within the interval such that the slope of the tangent line must be equal to the slope of the secant line. Now, how do I write that? Well, rise over run, right? Rise over run. So the way I'm going to write it is this: f of b minus f of a over b minus a. Right? Let's see. Where did that come from? Okay, so we said we had a function. Here was a, here was b, right? I plug in, that's f of a. I plug into another point on the function. Here's f of b, right? And then I'm trying to connect them, so I'm trying to find the slope of that line. What's the rise? It's the difference between the y coordinates, right? y2 minus y1. Do I remember that formula way back? y2 minus y1 over x2 minus x1, rise over run. So the y2 is f of b, the y1 is f of a, so that's this minus this, over x2 minus x1, b minus a. Do y'all see that's all that is? It looks ugly, but that's the slope of the secant line. It must be equal to the slope of the tangent line at some point c. It has to be there. All right? Questions? Yeah, now let's actually see a problem. Let's do a problem where what we're going to do is verify that the theorem is true. So verify this example, verify the mean value theorem for f of x equals x to the fourth minus 3x squared plus 1 on the interval -1, 1. I'm completely making this problem up. We don't need to graph it. We don't need anything. All we need to do is verify that this is true. Okay? We're going to need a derivative, all right? Remember what I'm going to try and do here is show. I need to show you. I need to prove that there's some number in this interval that will make this true, right? So I need to show you that there's some number between -1 and 1. Right? This is A, this is B. I need to show you that there's some number in between these that when I go to that number and look at the tangent line, it's going to be equal to, the slope of the tangent line is going to be equal to the slope of the line connecting the two endpoints of this function. So since we need the derivative, let's go ahead and take the derivative now. Let's just have it on our workbench so we can use it here. That's it? Pretty clean derivative? All right. The left side of this equation is f prime of c, right? We don't know what c is, so let's actually just write down what is f prime with c plugged in. Ah, shoot. Hold on a second. No, this is going to be too hard to solve. No, change this to a 3. Let's make our lives a little easier. Sorry. Change that to a 3. And then that'll change this to 3x squared, right? I'm just making it where we can solve it. I don't want it to be an algebraic nightmare in a minute. All right, so what is the derivative at c? I just rewrite this with c instead of x. Okay, and so what I'm doing is I'm rewriting this equation right here. And I'm going to try and check to see if it's true. If I check to see if it's true, then I have verified the mean value theorem. So let's plug in 3c squared minus 6c. I need that to be equal to what? F of b, which is really f of 1, right? F of 1 minus f of -1 over b1 minus a -1, so that's going to be really 1 plus 1. A and B here. Oh, this is the mean value theorem right here. This is the mean value theorem. Slope of tangent line at some point is going to be equal to the slope of the secant line. So now I have to figure out what's f of 1, what's f of -1. So what is f of 1? Plug 1 into this. So I have 3c squared minus 6c equals, what was it? 1 in there? -1. What's f of -1 plugged in? So I'm going to go minus, right, minus f of -1. So -1 here gives me -1. -1 squared there, doesn't matter, it's still 1, so -1, and then, or -3 and then +1. So what do you get? -3. So it'll turn out to be +3. All over 2. So we actually get, the right side is -1. Oh, I forgot to put the parentheses here. That looked weird. -1, +1. This is 1 plus 3, right? 2 over 2, +1. So here's what I have. I have this. I have that 3c squared minus 6c needs to be equal to 1, right? In order for this thing to be true, in order for this mean value theorem to hold, I would need that to be true, wouldn't I? Which means I need to figure out what c's will make that true. And that's just a quadratic equation, isn't it? Can you solve that for c? Yeah, so that's what we're going to do. I'm going to do 3c squared minus 6c minus 1 equals 0. Now, let me ask you something. When I solve this quadratic equation, should I get an answer between -1 and 1?
Yes.
Yes, the mean value theorem guarantees it. Guaranteed it should happen. Well, as long as f was continuous and differentiable. I didn't even talk about that, did I? My fault. It's polynomial, so I figured you assume that, yeah, polynomials are well behaved, aren't they? Derivatives of polynomials are good. So, all right, solve. Quadratic formula, right? You could do that. If I use a quadratic formula, I would get c is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And I'm going to go get my calculator. I don't think that, I didn't even bother to look that it factored because I made up this problem. I just made it up like out of my head. And the chances of me making up a problem where this works out to be factorable are pretty slim. Although in my last class it almost did.
You did it in the beginning, you like 3 times in a row.
Yeah. So I'm solving. Can I trust that everyone could solve this? Is that within appropriate expectations?
I would hope so.
I hope so too. All right, so I'm getting 2 answers. All right, one of them is c is equal to negative 0.154700, and I've got more numbers, but that's good enough. And the other one I'm getting is c is equal to 2.1547, blah, 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 some more decimals over there.
Submit the second one.
Yeah, so now what we're going to do is we're going to say, okay, we were trying to find a c, there's got to be at least 1 in here, right? At least 1. We found 2 answers, and one of them lives in here, right? The other one doesn't. So the mean value theorem guarantees us the existence of at least 1. Here it is. Now what this means visually, graphically, is this. If I graph that function, right, if I graph it, it was the function x cubed, what was it? Minus 3x squared plus 1. If I graph that on the interval -1 to 1, there it is. I'll erase some stuff. There's the graph of that function on just the interval -1, 1. And I imagine connecting the 2 endpoints with the line. Right? Imagine connecting the 2 endpoints. There was some point on the function where the slope of the tangent line should be parallel to that. And we said it will happen at c is -0.147. So -0.417, or sorry, -0.1547. I don't know, somewhere around in here, wouldn't you agree? Something in here? You go up and you get the slope of the tangent line, it should be parallel. Now I can actually have the computer do that for me. I can have it draw me that tangent line. So I'm going to do it. I want a tangent, and I want it at -0.1547. 7. There it is. See? The average value of this function is the slope of that line. Somewhere within the function, we achieved the average value. The slope of the tangent line was equal to the slope of the secant. So when you get a problem like this, I hand you a function, I give you an interval, I say verify the mean value theorem. You take the derivative, you plug c into it, you figure out what f of b minus f of a over b minus a is, that's a number, and then that equation you have to solve for c. That equation could be quadratic, it could be linear, it could be, well, that's why I said practice these problems. So page 215, numbers 9 through 12. Did anyone not get this? Those are some good practice problems. What do y'all think? It's kind of an interesting theorem. No comment? All right, let's talk about the cars racing. I said we'd come back to this, right, at some point? Now we'll talk. All right, so see if you remember the question. We had two cars, car A. This is a top view. And there's the starting line, and here's the finishing line over here. And green light, boom, they go, right? They race, and at the very end, when they get to the finish line, they both cross the finish line at the exact same time. It's a tie. They tie, right? So they have to have the same average speed, right? Because they both covered the same distance over the same interval of time. The question is, does it happen at the same time? Since they both have the same average speed, that means that because of the mean value theorem, at some point in time, you look down at your speedometer, you have to be going that average speed. So the question was, is there a point in time that both of these cars were both going the same speed? Same point in time for both cars, that they're going the same speed.
Their endpoints would be parallel.
Not at the endpoints. Sometime within the race.
The moment they move,
Everyone understand the question? Okay. What I'm going to ask is for a vote, all right? And I'm not going to give you any credit if you get it right or take anything away if you get it wrong, all right? So how many of you think that, yes, there is a time, some point in time, and it's the same point in time for both cars, that they will both be going the exact same speed at that same moment in time? Yes. 1, 2, 3, 4, 5, 6. Okay. I'm hoping everyone's voting. And then that means everyone else is no? I want you to put your hand up. I want you to stick to it. Yes? I mean, this is a no. This is no. No? Okay. So now, volunteers from someone who said yes. Try and convince these no people.
the moment they move, they have to have some sort of speed.
What if the first car doesn't move and waits for the other guy to take off?
Their speeds increase or decrease, but at some point they have to cross.
Which one are you? Are you yes or no? You're yes? Okay. Hold on. Say it again.
They're increasing and decreasing in speed throughout the race, but at some point they have to cross. They're going to finish at the same time.
Well, what if this happens? What if this car takes off, okay, and this one waits and then takes off, and then right at the end of the race they tie? Do you see what I'm saying? I'm just arguing with you on purpose.
Because we have a starting time, like we give a green light, because B is stopped and A is going, because B is just at a stop, it's going to average into the speed. So you're just going to be at 0, you're going to be stationary for a while, and then because you accelerated, it's going to average out. Does that make sense?
I don't know. You're not trying to convince me. I know the answer. But, okay, how about someone who says no? Were you saying no or yes?
I'll say yes.
Okay, how about someone who says no? Convince the yes people that it can't
At
happen.
a specific point of time, right?
Yeah.
I feel like the both of the graphs are different, and the mean value theorem only guarantees that the c is equal to the average speed.
Okay.
So even though they have the same average speed, they have different graphs. So
Yeah.
won't guarantee that it'll match up.
Let me try and draw what you're saying. I think this is what you're saying. We have two cars starting here. Let's say they both end here. Okay, so this is time and this is distance. One car can do anything it wants, right? It's got to end up there, right? And the other car can do anything it wants. So I'll draw it like to the extreme here. Like that. All right?
You have an average speed somewhere.
They both have the same secant line, right? They both have the same average speed, which would be this. So if you look at the red curve by itself, the mean value theorem says there's some point in time for just the red curve that I should be parallel to the blue curve, right? At least once, right? At least once. And that could be, I don't know, visually, would you think, maybe around here? That would run parallel? Is that a good, that's at least one of them? Then, if we look at just the purple curve, the mean value theorem applies again, and we say that there exists some point in here where the slope of this tangent line must be parallel to that, right? But does that have anything to do with this one? No. I think that's the argument you're making. So the yes people, any counter arguments?
It'd be the same.
I mean, I can see how you could confuse it and think it would because all the lines would be parallel. But
What do you mean all the lines?
all the lines, both the tangent lines of both cars and the secant line are all going to be parallel to each other.
Yeah, they're all parallel, but are they happening at the same place?
Right. I was just saying that I can see how you can confuse it though.
Yeah.
The question was,
Yeah.
do you have the same average speed at any time, right?
Pardon?
The same average speed at any time, correct? Well, that was the question, right?
No, I just said, is there any point in time where they both look down, their average speeds, their speeds are the same? That's what I said. And it's got to be inside the race. Okay, so look, the reason why I love this example so much is because I think there's good arguments both ways. I think there are some valid arguments for yes. I think there are some valid arguments for no.
What does math say?
And that's where what it comes down to. Like, how do we figure it out? And this happens in the real world a lot also. You have a problem. You've got one person who say, yeah, I think this will be, this is what it is. Another person, they both have pretty decent arguments. And you really can't wrap your head around the problem because, look, this problem, there's too many different scenarios that could happen, right? All these different variations of the race could occur. How could we possibly take every one of them into account? Yeah? So at the end, we need something that's going to be the say-all, be-all answer, right? And that's where mathematics comes in. And then there's no arguing. The correct answer is yes. All right?
Yes.
Now, how do we show it? Now, I'm going to show it to you, okay? You ready? I'm going to prove it to you. And I'm going to prove it to you with that picture right there. And it's going to be a little involved, okay? So let's see if you can follow this. And go back to that picture right there. I'm going to call the red curve F, and I'm going to call this purple curve G. All right, everyone? And let's just be clear on what I'm trying to show you. All right, if I can convince you of this, then you will have to say, yes, it happens. I must show there exists, but that's the mathematical way that we write there exists, okay? Instead of writing the word there and exists, there exists a C in AB such that we like to write ST instead of such that. This is the way we do it. I'm serious.
Is it really?
I'm completely honest.
I already forgot what that's.
This is for every, and I should have replaced this mathematically with this element of this interval.
Oh my god.
It's a language, people. It's a language, okay? It's a language. It's a shorthand, all right? It makes it a lot easier. So when you open up these math books that are all complicated, you look at them, you're like, what the hell's going on here? It's a language. It's like opening up a Russian textbook and being like, what is this? Well, you have to learn the language. So I'm sharing with you some of our language. There exists a C in AB such that, what would I need to show you? Or what would I need to convince you of? How about this? That the derivative of f at C is equal to the derivative of g at C. Isn't that what I would need to show you?
Yes.
Right? So anyone argue with that? If I can show you that there's somewhere in here, C, where the slopes of the tangent lines on both functions are the same, you'll be satisfied. Yes? Okay, a couple of other things we need to get out of the way before I show this to you. If you have a continuous function and you add another continuous function to it, is it still continuous? Yes. Now we covered this back when we were covering continuity. So two continuous functions added together creates a new function which is still continuous. Two continuous functions subtracted from each other still has is still a continuous function. That okay with you? Sure? All right. The next thing is that when you take a derivative of a sum, you can take the derivative of each one separately. We've done this before, haven't we? We take derivative of two things, you do them individually. That's all I need, and I can show this to you. All right, so here's what I'm going to do. I'm going to, let's label this A, and let's label this B. All right, the two endpoints. Just so we're all clear, what's f of A? 0. Right? But that's also f of B, or g of A, isn't it? F of A and g of A are the same, right? And what about f of B? It's equal to g of B, right? I'm just writing this down just so we're clear on it. The value of the two functions at the two endpoints are the same. That's because they start at the same point in time and they tie, don't they? That's what this says. All right, here we go. So I'm coming in here as a person trying to convince you who are skeptical of this. I'm going to this is kind of like a little bit of a God complex that you get in mathematics. So you have this ability to create what you want. So I'm going to create something. I'm going to let a new function h be defined as the difference between those two functions. All right? I'm going to subtract the two functions from each other.
Why would you subtract them? Is that because you're going to set it to 0?
Nope, just watch what happens. This is one of those things where this is not a natural thing. Okay, this is not something you would just go, oh sure, just subtract the two functions. But something really nice is going to happen, all right? Watch what happens. What is h of A? Then h of A is, okay, we'll plug A into this and plug A into this, right? What's f of A minus g of A? What's f of A minus, they're the same thing, aren't they? 0 minus 0? So this is 0. So h of A is 0. Agreed? And h of B is what? F of B minus g of B, but they're the same values. So that's 0, right? And h is continuous on AB. All right. Why is h continuous on AB? Well, because the two functions f and g were continuous. Because you're not in some sort of teletransporting car. You actually have to go from point A to point B, right? Your speed can't just change like from positive to negative like that, right? So this is a continuous function. And let's draw it. Let's draw this function real quick. Let's draw it right here. What does h look like? What's h of A? 0. What's h of B? 0. And according to the fact that it's continuous means I must be able to connect these two together with a curve, right? So let me draw a curve connecting these. And it really doesn't matter how I draw it as long as it's continuous. Doesn't matter, right? Rolle's theorem tells us that there's got to be a point somewhere in here where, let's call this C, the derivative of this function must be what at this point? 0, right? Parallel to the line connecting these two. Understand? So by Rolle's theorem, there exists a C, an element of AB, such that H prime of C is 0. There's got to be somewhere in here where this was the graph of H, right? Where the derivative at that value must be flat, must be 0, yes? So no one's arguing with me? I want to make sure I don't want anyone to be skeptical here. There's got to be a point in here where the derivative of that function h at that point is 0. Yes?
What are you using to measure time? Because they have to be at the same time.
What do you mean?
The same speed.
I'm not done yet, okay? All I've done is I've said, hopefully with some logic that you're following, that there's got to be some point in time where the derivative of h is 0, right? Okay, now what is the derivative of h? Go back to this, right here. I got to move up here. So from this right here, therefore, more math symbols that you don't like, therefore,
Looks like the laser on.
that is the predator, the predator's sights. No, that is actually the technical way that we write therefore in math. You want to write therefore? I don't. Well, I wouldn't. It's just the way it is. Okay, just the way it is. Okay, so therefore, to say that h prime of c equals 0 is the same as taking the derivative of this, right? Which is this. What's the derivative of this with respect to h? H prime of c, h prime of x equals f prime of x minus g prime of x. If I told you to take derivative of this, you would just take derivative of each one, right? Therefore, h prime of c being 0 means that f prime of c minus g prime of c equals 0. Right? If I say h prime, don't I really mean f prime minus g prime? Okay? So to say h prime of c equals 0 says that f prime of c minus g prime of c equals 0. I'm almost there. What do I do? Just some algebra here. Move that to the other side. F prime of c must equal g prime of c, which is what I wanted to show you. You told me if I could prove to you that there was some point c in there where the derivatives were the same, you would be happy. And I just did. All right, so if you didn't follow that whole thing, I'm not going to test you on this or anything. This is just to get you to see, like, this is a way that a theorem like that can be used to answer a very difficult question. And this is the way a mathematician would approach it. The question I think that would still remain is how would you have come up with this? Right? How would you have known to come up with this function?
Not really intuitive.
It's not. And so that's what mathematicians have to do. They have to find ways to break these walls down. And they attack these problems with different sorts of just keep going after it with different things. This problem actually came out of, now the problem that I saw in my book when I was in school was not in terms of two cars racing. It just said, F is continuous on AB and G is continuous on AB. Show that there exists a point somewhere in there where the derivatives are the same, okay? And so I had to do this, and I had to come up with that on my own at some point. And I remember this is one of the first problems I did where I was like, whoa. Like after I figured it out, I was like, gosh, this is going to be tough. Like, how do you figure this stuff out? So, yes had it. So yes, the answer is yes. Weird. How do y'all feel? Who cares? Let's move on, right?
I'm still trying to figure out how you
Why
got
you
the
just
h of
did
x is f of x minus g of x.
Because it worked.
I'm trying to come up with a name for it.
Well, look, here's one way that you can be motivated to have gotten that. You start drawing enough of these pictures. You start drawing different variations. And you realize, you know what? If I look at the difference between these, like the distance between the two cars, right? I know that at the beginning, the distance between them is nothing, right? And then the distance grows and shrinks and eventually has to go back to nothing. And so maybe the first car has the lead the whole time. And so, you know, eventually distance has to go back to 0. And then you go, oh, wait a minute. If I look at it that way, then somewhere in here this is flat, and that corresponds to somewhere in here where they're parallel. But I can't tell you how that happens for everyone. All right? So your concept of what math is, all right? In everyone's minds, when they come into math classes, they have this idea of what math is. You get to calculus, have this idea of what math is. Same thing I thought when I was sitting there. What I just showed you, that's what math is. That's what mathematics is. When you get to, like, you know, you think, like, what does a junior do? A junior level math class look like? It's problems like that, where you're proving theorems, you're trying to prove things abstractly, and it's not for everyone, but for some people it's enjoyable. I just happen to be one of those people who enjoyed it. So, all right, I'm trying to find some math majors in here that can get excited about something like that. But
I think it's cool.
you know,
Chemistry major, so.
all right, what are we gonna do now? I've almost eaten up the whole class here. Y'all ready to do Newton's method? Newton's method. Now it's different section.
What section is this?
4, 5.
Do we not like have any problems for the mean value theorem? It's just like that, just a concept straight up.
No, the mean value theorem, the problems that you would face would be the ones like on page 215, number 9 through 12. Those are problems you should look at. All right, some instructors don't do this section, Newton's method. It's 4.6. But I want you to know about it, okay? I want you to have seen it. I'm not going to test you on it. I might offer it as a bonus. But that's about it. But it's important that you understand that this thing exists. Some of you have some pretty fancy calculators. And some of you know how to use them. And you can use these to solve equations. So like if I give you an equation like this, solve x to the 5th minus x minus 1 equals 0. Solve that equation. Then some of you know how to do this on the calculator. I'm actually going to do it right now. I'm going to use this feature on my calculator called solve. And I type it in. And just like that, hello, come on. That took a little while. It took a couple of seconds for the calculator to spit this back to me. I got x is equal to 1.167303978. I'm showing you all the decimals. All right, that's what it gave me. So what just happened? What did this thing just do?
It's all for where x is 0.
Yeah, but how? How to do that?
It's a program, an algorithm.
Yeah, what is the algorithm doing? Any ideas?
It's probably like
It's sitting there going, it's looking at it going, no, it's not a quadratic, so I can't use a quadratic formula. No, this thing knows zeros and ones. What's that?
Is it graphing it and finding the x-intercept?
Graphing it and finding the x-intercept. So the way your calculator graphs, when it graphs something, all it does is starts plugging numbers into this. Just like plugs them in and just starts spitting them out. And it does so many of them that to you on